Hi, I'm Yash, and we are a group of researchers from Tufts University and GTRI here to present our work on a framework for few-shot policy transfer through observation mapping and behavior cloning. Policies trained in a simulated environment cannot directly be transferred to a realistic scenario. This is due to the fact that physical robots usually have noisy sensors and actuators, and exactly matching the simulator to the physical setting is quite difficult. In this work, we intend to perform a policy transfer from the source environment to a realistic target environment, even when there is a mismatch in the observations and the actions of the robot. This is especially important as the simulated environment will always fail to truly and accurately model the real world scenario due to several unknown parameters present in the real world setting. For example, if the source task is a simulated robot navigating to the green cube, and the real task is a physical robot navigating to a different colored cube, our work aims to learn a policy in the source task and transfer this learned policy to the target task, even when we do not have an explicit mapping between the two environments. Our approach can be divided into three distinct components. The first component involves training a policy in the source task. In the sim to real scenario, the source task is the simulated environment, and the policy maps an egocentric robot image to an action that navigates the robot to the cube. The second component involves generating a mapping between the source and the target environments. This mapping is obtained by initially collecting images from the source and the target domains and training a cycle GAN that produces two generator functions that map images from the simulated environment to images in the physical robot environment. CycleGAN does not require an explicit label mapping between the two datasets and learns two functions that map the images between the two domains. The final component involves training a policy for the physical robot. We instantiate the simulator and compute the action from the learned source policy. For the simulated image, we also compute its equivalent realistic image from the generator function of the learned CycleGAN mapping. Next, we behavior clone this computed action from the learned source policy to the action generated from a randomly initialized target task policy using a cross entropy loss. The behavior cloning procedure produces a target task policy purely from the GAN images and does not require any training in the realistic target domain. This policy is then deployed on the robot in the physical robot domain. We initially experimented on a sim-to-sim domain with mismatch in the observations between the two domains. The target domain is semantically similar to the source domain, with only difference being the colors of the objects in the domain. We observe a 94% success with our proposed approach beating the two baseline approaches. The cycle consistency loss of CycleGAN encourages a pixel-wise consistency of the images in the source task and the adapted source task image generated with the help of the two generators. The graph on the right shows that the transfer success increases with an increase in the number of images in the source domain. On x-axis, we have the number of images in the target domain that were used to learn a CycleGAN mapping, and on the y-axis, we have the success rate of the behavior clone policy on the target task. We observe that a success rate of 75% is achieved with only 400 images from the target domain. For the sim to real task, the target domain is a physical robot, turtlebot, navigating to the cube in a walled environment. Along with a mismatch in the observations in the environment, there is a mismatch in the actions as well as the goal. For example, a move forward action in the simulated environment moves the robot ahead by 10 centimeters, whereas in the realistic environment, the same move forward moves the robot ahead by 5 centimeters. Even with mismatch in the observations, actions, and the goal, we observe a 90% success rate on transfer. To conclude, we introduced a novel method that proposes successful few-shot transfer with limited data points from the target domain and also incorporates observation and action mismatch. In future work, we would like to address the problem of cross-domain knowledge transfer, where two domains do not have an explicit mapping in their Markov decision processes but are semantically related. Thank you for your time, and here is the QR code for our paper.